Welcome to the channel where all you gotta do is a little CAD spin of this Mustang resto mod I'm designing and building. So it's been kind of cold and wintry around here the last 2 or 3 weeks, so I've been spending quite a bit more time playing in CAD. Another reason is I have spent a lot of time in the past few months scanning parts, upper control arms, lower control arms, differentials, uprights, stuff like that. So I kind of got all the puzzle pieces in place so I can start actually designing the rear suspension. Front suspension is pretty conventional. I'll go over that a little bit. The front suspension is traditional double wishbone A-arms. Nothing super fancy about it. The uprights I'm using are from a McPherson strut design, but I'm not going to go with McPherson struts because those are stupid and they're designed by the bureaucrats of the finance, whatever. There's no redeeming qualities really other than they're cheap. My opinion, I could be wrong. So this rear suspension, however, BMW didn't really spare a lot of expenses on it. It's pretty complicated. Unfortunately, I have different constraints than they did. And my constraints didn't allow me to utilize what they had. So I I didn't scan, but I measured the rear subframe. These are the lower control arms here. Scanned. This is the upright scanned. Let's hide this guy because that's kind of an older design. But one of the challenges that I had with using this suspension stuff is this is where the shock absorber, like normally the shock absorber is here and then it goes up to here and then the spring is up, into the trunk area. And I have quite a bit of room between the wheel and the frame rail, so I was trying to, put the shock absorber in here somewhere, but there just wasn't room. I mean, I tried 5 or 6 locations on where I was going to put the shock and trying to find a decent double adjustable coilover that had, it just wasn't working. I even resorted to a bell crank setup, but this didn't work either because the bell crank chopped through the frame rail and it still took up area inside the wheel well that I didn't like. So that wasn't great. The other thing that didn't really work out for me very well is if I turn this diffuser on, the suspension at full droop, and as you can see, the suspension arm is kind of not in a good place. So the other challenge that I had was fitting the shock absorber in there, and even with the new relocating shock mount, it went right through this control arm. So that wasn't going to work either. I basically kind of had to come to the realization that I just needed to abandon, even though I like these lower control arms, they're nice hollow casting, they're fairly lightweight and stiff. And you need it to be stiff in torsion because of the way this suspension works. This thing is in twisting, right? When you put load, like the forces going to push the car to slow the car down, this one has a reactor force on it, right, pushing forward, and this one's pulling up or pushing down depending on accelerating or decelerating, but it doesn't have any side load. So the front of this just has a link, so it can't transmit any force in and out. It can only transmit force up and down. So that means that all the loads have to go through either this and this up and down. So now this has to have a box section. You can't have like sticks, right? You have to have something closed to get it strong and torsion. The other thing that discarding this lower control arm did was these are both on angles. Like this is on I think it's like 9 degrees, and this is like 45 degrees. So when this thing pivots up and down, these are both binding. So this one is a lot stiffer, right? This is doing most of the work. But this one, in order for it to not bind, has to have some flex in it. And flexy lower control arm bushings are not good for super sticky 315 tires. So I kind of weighed all the possibilities and outcomes and how much extra work it was going to be to make these mounts sticking down as far as they are. It was going to be a really heavy structure to get the. Yeah, this is like a cross member that I kind of came up with, but from the frame to where the mounts are in the rear, you have to make this giant structure, and then in the front, it's this complicated, massive structure as well, and that's not even getting into the upper control arm stuff and the fact that the shock absorber goes through the axles, and it just wasn't. I spent way too much time on this, and it just wasn't. It wasn't solving. So the plan verified was plan verified as far as the brakes fit and all that stuff. But when you run into a roadblock in a design scenario, you have to give up when it doesn't look like it's going to work. I mean, I could have made it work with a big heavy structure here and intruding into my area that I may want for wider tires, or I definitely want I don't want big shock absorbers sticking in my load floor. So basically what I did was I abandoned using the lower control arms, and I just designed my own lower control arm. So it looks like that. It's a little bit heavier than the stock one. That's with this bar going through it, but the stock one's I think 9 pounds. So this does have some other features on there that I'll get into maybe in another video. But oops, cancel, make it big, don't make it go away. There also used to be a cross member in here, which I kind of just moved down, so I didn't have to make a whole new cross member to hold the lower control arms. And then the front cross member, which isn't really a cross member because you can't remove it, but it's part of the differential mount. This is the differential front bushing mounts and the control arm mounts and some frick mount stuff. So that's pretty tidy. The other thing that I haven't really elaborated on yet, because like I said, I'm going to bounce around a bit, is I wanted to not have the shock sticking into the load floor area. So what I ended up doing was making a bracket, this bracket right here, which is, nothing fancy, and it weighs, I don't know, 1.5 pounds or something, so it's not super light. Unsprung mass, I don't like adding that, but what that did was allowed me to put the shock in here. So now, where my tire is, the shock doesn't get in the way of it. The rim's actually bigger than that. So I can fit my shock absorber in here. And this is a Koni 8212-1121, which is little over 5 inches of travel, and it's double adjustable. Double adjustments are here, and there's you put a pin in here and adjust it. So this is that link I was talking about, right? So this can't transmit any force in and out. It can only transmit force up and down. It's like an articulating link. And what that allows this rear suspension to do is this controls the toe in. This is the upper control arm, really, but this one kind of shares responsibility, but not really, because it's on this link here. So this is basically your toe link. This is your upper control arm. And then the way this is constrained is like the lower control arm, because it's in torsion, acts like the lower control arm plus sort of the upper control arm, because it can only articulate in one direction. And then this is just the link that holds it, holds the top in place. And then this one makes it so the front and back, or so the toe in can be manipulated. And you can change the length of this and forward, aft, and up, down. And that changes the geometry a lot. So if you move this link, you know, a half an inch back, it'll screw up your camber and caster curve, toe in curve. It'll fuck everything up. Which brings me to, you're probably wondering what these little sticks are over here. So I use SolidWorks as my suspension geometry designing software. And so the way I use this is I get it kind of close by articulating the wheel up and down, and you can see the negative camber in here. And if you zoom in really close here, see this little pokey thing sticking out right here? That's the thing that sticks out in the front. So you can see there's a tiny bit of toe in here. And that's just for visual references. Once I get where I'm kind of reasonably happy with it, then I come down here and turn the ground on like that. And then I use my little tape measure over here, and I don't pick the surface, I pick this line and this plane, and then that gives me my toe in. In this position it's 0. And then if I want to know what my negative camber is, I pick this line and this, and I got 0.9 degrees at this ride height. Obviously it changes, and I have I just move the shock 1/4 of an inch travel, and see, we got that right here. So if I just change this minus 0.5, boink, that moves my suspension up. Of course, the solid model doesn't, or the scanning thing doesn't move up, but just ignore that. And then I can take another point, right? I can go back and I can measure, and I can go, okay, there's my that, there's my that. Now I have 1.77 degrees. And if I want my toe in, I measured from there to there, and I got 0.04 degrees. So that's how I do it. You got to get fairly close first, and all the positions and lengths of these links matter. Now I also have a spreadsheet that, before I go to the spreadsheet, I also have, just to get kind of close, I mean, we live in a 3D world, right? But you can approximate stuff with 2D just to kind of, so here's my name of the file is front geometry. We'll just open that up. It turns out this is not front geometry. This is front geometry here. This is rear geometry. So I picked the location, like this is kind of overcomplicated, but all these points here are the positions of my upper control arms. This is the rear arm, not the toe link. And this is the lower control arm, and that's wheel size and whatever. And so I pick the height from the ground to the shock absorber as my driver. So if I make this 18 inches, that'd be 1 inch of bump, but not wheel bump, that's at the shock absorber. And as you can see, my roll center changes. The instant center of the suspension is here and here, but my roll center going around the corner is there. And really this wouldn't happen. You wouldn't hit a bump on one side necessarily. When you're going around the corner, it would do more like that, right? So that's what my instant center does, and that's the distance from the ground. So this is how I do it. I get close with this, and then I can plot this out in an Excel file, and I can look at my toe-in curve and my instant center, and you know, I can graph all that stuff. What I really care about is this number here and this number here. So when you're going around a corner, this isn't your ground anymore. This is this dotted line. Essentially, you just shifted your reference plane. So, and from that plane to this wheel, and this is the one that's in bump, right? So this is going to be the outside. So in this, looking at the back of the car, we're turning right. I still have 0.8 degrees of negative camber, right? On the inside, unfortunately, I don't have, right? You would really want this to be over 90 degrees. It's really hard to do that with, you have to make compromises in this to get that to be negative. You have to have such an aggressive negative camber curve on this side then to get this one to be what you want. Like you'd really want this one to be, you know, 90.7 or something like that. But this one's doing most of the work. So you prioritize making this guy happy, and then this guy's like, well, it's less unhappy than most production cars, but it's still, I got 2 degrees wrong of negative camber. So that's how I do it. So we should just go over this because it's very similar to the toe-in curve. But basically, the only kind of car that has perfect Ackerman is a Radio Flyer wagon or a old-timey, you know, from Bonanza, a wagon where there's just a pivot and these are on the same angle. Right? That's the only time you really get a perfect Ackerman. Now, I did design something in college that gave the super mileage vehicle perfect Ackerman, but maybe that's a story for another day. But basically, you take the axis of the outside wheel and the axis of the inside wheel, and you present those out to infinity. And then you have to know your wheelbase, right? This is your rear axle, assuming that goes straight. And then when you rotate this guy, like that there, if you have perfect Ackerman, this guy, and the rear axle all line up at the same point. As you can see, that isn't the case here. But I could make it very close if I wanted to, but I don't want to. And the reason for that is tires don't roll straight. There's this thing called a slip angle, where when you turn let's say you turn the wheel 2 degrees, your car only changes direction 1 degree. Making these numbers up, but you get the picture. There's a flexure of the carcass of the tire, and that's what provides the force. Like if it was going perfectly straight, there would be no force generated. It has to have a slip angle to generate force. And it turns out the more downward force you have on the tire, mu times normal force is what gives you the traction. The more normal force you have on the tire, the higher slip angle you can tolerate without breaking adhesion. And since the outside has more, as you're going around a corner, it has more normal force because center of mass is above the ground, so that weight transfers to the outside wheel. So you always want to have, in my opinion, now if you're making a super mileage car, no. But if you're making a car that's supposed to be, you know, higher performance especially in cornering, you want to have an over Ackerman design, which this is. This one is, if this was perfect Ackerman, this would be over here, and this would be less steer angle on the outside one, or more steer angle on the inside one. So I've done that on purpose. The Sonda does the exact same thing. The Bronco does the exact same thing. But it's done on purpose. To really get this tuned in perfectly, and like, you know, your Formula One guys or your, you know, professional racing series, they have tire curves for the exact tires they're running at different pressures, at different normal loads. I don't have that information. But most tires are kind of in the ballpark of each other. So you just have to understand that a little bit more steering angle on the outside wheel is gonna tolerate more slip angle before it loses contact, or you get to a dynamic coefficient of friction versus a static coefficient of friction, which hopefully we all understand that. Once you lose traction, your traction goes down, right? That's why anti-lock brakes work. They get to the limit of adhesion, but don't go over it. Because when you go over it, now your static friction goes to kinetic friction, which is, you know, a third less or whatever. Depends on tires, road surface temperature, everything, but it's less by a significant amount. So anyway, this is how I do it, but you have to have enough information to put into here. So you have to know, for instance, this 24.4 inches, that's the width of the rack and pinion that I'm going to be using. Like, that's where the pivots are. Now, it doesn't mean you can't change it. Like on the Sonda, I changed it. And the Bronco, I changed it as well. As a matter of fact, on the Sonda, not only did I change the length of where these ball joints are, I actually flipped the rack upside down because it was a rear steer. I stole that rack out of a Saab 9000, and it was like the steering rack was behind the axle, not in front of it, which I'm not sure how they made that work. Maybe they didn't, because I tried really hard on the Bronco project to make the Ackerman work with a rear steer, because for obvious reasons I didn't want rocks to get bashed into my my steering arrangement in the front. So I tried to put it in the back, kind of to protect it from, you know, getting bashed by rocks and shit, boulders, logs, whatever. And I just could not make a decent Ackerman curve for that. So anyway, this is what goes into it. I don't use fancy software. I do want to say that this is a 2D representation. So this will get you into the ball field, right? You'll be playing the right sport. You'll be in a soccer field instead of a baseball field, but it won't be where you want to be in that field. Once you get this geometry sort of sorted out and happy, then you have to go back and put everything into 3D and then do the same thing I did on the rear suspension, right? You have to go through and you know, bump this up 1/4 inch at a time, take the measurements, right? Because everything is articulating, and like the height of this, like it doesn't show up, but the height of the steering rack, if you move that up an inch or 2 inches or 5 inches, you're going to completely screw up your Ackerman steering curve. So you have to start somewhere though, right? You have to get all the pieces that you're going to use or plan on use, and then put them into, I mean, you could write a spreadsheet. I find using a CAD program is really good for complex geometry, especially 3D geometry. And SolidWorks is nice because you can articulate it and see it kind of move when you move the mouse around, and you kind of understand what's happening. I'm a visual person, so I like that. But you could use a dumb CAD as well, or you could write a spreadsheet. This is how I do it. Doesn't mean it's the right way. It just means it's the way I do it. Okay. So this is the geometry that on the rear suspension, and this is the toe link, and this is the height of the toe link from an arbitrary place, and I changed it from 2 3/8 of an inch to 2.5 inches, and this is the change I got. Right, this is the toe curve, and you can see it's quite a bit flatter. Right, from here to here, it's very close, and it's you can see it's quite a bit different. And this is the camber curve. Didn't change much. The toe link doesn't change the camber curve. So this is what you have to do, right? You just have to, move stuff around and do some calculations and figure out whether that move that you made is what you want. And when it is, keep it, or at some point you have to shoot the engineer and build it. So you can optimize till you're blue in the face, but typically, I don't know, 4 or 5 hours of fiddle futzing around, you can usually get to a pretty good solution for what you need. I need to go over here, but I don't know if you can see this weird shape of the lower control arms. Well, that's not just because I slipped. I turn the diffuser on. You'll see that is intended to clear the diffuser. Even at full droop, it still clears the diffuser. So, not by a lot, but that was a main kind of a criteria for what I wanted as a solution. And the stock ones didn't do that. You can also see that the upper and lower control arm pivots are in a straight line now. So this thing just pivots straight. So that's nice. And then it's pretty tidy how I've, the links don't have extra bracketry, heavy bracketry coming off of them. So while we're playing in here, might as well take a look at the roll cage. I've done some videos on what the roll cage look like. So this should, if you've seen some of my previous videos, this should seem, you shouldn't be surprised by it, right? These are the floor plates. This probably looks like the floor plate that you saw me build. I still need to put the pedal assembly in here. I haven't scanned that yet, so. But yeah, this is the cage that I'm intending to build. I've already built. I don't know if you can see. We'll put a side view in here. Yeah, you can see the kickback that I have, which was, it was harder to make that way. And then I have some down bars, a couple of sets, and they're triangulated, so they give some stability left to right as well. I've done something a little bit weird on the diagonal bars. I've made them go forward. And the reason I did that is because I'm a crazy person. Tidy up this. So these are my fuel cells. So they have to kind of go around the fuel cell, and this is going to have a load floor in here. So it's going to be a hatchback, so it's going to have a load floor. So now I have all this extra area that I don't, I'm not wasting it. I'm limited by how tall something can be in there because of I think it's like 9 inches, but toolboxes and jack and stuff like that, you can totally stick in there. So anyway, that's what the roll cage looks like. Front suspension, kind of similar to double A arm. Nothing magical about it. Same shocks front and rear. I do want to touch a little bit on ball joints because there's basically 3 types of ball joints. There's ball joints that you can load in tension. So that you're trying to pull the ball out of the socket. And there's ones that you can load in compression where you're pushing the ball into the socket. And there's other ones that don't do they just take side load. So this, I don't even remember what it's for originally, but I had to scour the internet to find a ball joint that would fit into this application, and it had the right size shank for this upright that I stole off the M6, and it cleared everything, and it was the right right. It's in compression, right? The spring force comes through here, and then this is pushing, the wheel's pushing up on that. It's pushing up on. So, and then this upper one, this one, it turns out this is a Chrysler ball joint. But this one is just taking lateral loads. It's not taking, there's no up down forces on it except for, moving itself. So you can't just select any ball joint. And I kind of learned this lesson the hard way because the Sonda has the same ball joint upper and lower on the front of a Saab 900. And so I just used those ball joints, upper and lower. Well, it turns out they loaded it in compression in production car, and I loaded it in tension. Yeah. Took it to the racetrack. That was really loose after 20 laps. So, we all make mistakes, but learning from them and teaching other people don't do that, is what I'm trying to do here. So anyway, make sure you use the right ball joints. Typically what I do is I search for a ball joint that a car of similar weight, because you can't just go ball joint, what size thingy is that, right? But if you go to Rock Auto and you search for a ball joint for a Honda Civic or a whatever, there's like pictures in there. And usually there's dimensions, depending on the brand. There's more. But you can get a dimension of the shank size. And if you find something that has the right taper angle, because these are all stupid 3.5 inches per foot and 2 inches per foot, how people do taper stuff, really, really, really dumb. But anyway, that's how they do it. And then once you find something that's kind of the right size, has the right angle, about the right vehicle weight, loading kind of stuff, then you can go, okay, what does the suspension look like, and see how it's loaded. Look where the spring is, look what the upright looks like, right? It's a whole bunch of extra work. It's I know why people just go to Speedway Engineering and buy spindles and ball joints that they know fit the spindle, because it's quick and easy. But it's also quick and easy to get a Mustang 2 front suspension, which, has anybody ever said, wow, I drove this Mustang 2 and it handles so awesome? It's a Pinto. Don't buy a Mustang 2 suspension if you want it to handle good. Buy a Mustang 2 suspension if you have a hot rod and you want to get a front suspension on it quick, right? That's what all the TV idiot shows guys do, because it's easy and they don't know anything about how to design a suspension, so they just buy something and assume whoever designed it knew what they were doing, which probably not a good assumption. Anyway, my opinion, I could be wrong. I'm using BMW parts and an S85, so what the hell do I know? Anyway, this is what the roll cage looked like. A little bit unorthodox with this little guy here. I got some little extra braces in here. This will be hidden inside the door. No, you don't ever see it. I got some little kickouts because this is a pretty long span for the door bars. So I'm still contemplating whether I want to make these door bars removable, but at this point I haven't decided to make it removable. One other thing here is I'm going to turn the engine on, and this is a really big file, so sometimes SolidWorks runs out of memory. Sometimes it doesn't. So that's where the motor lives, and it moves really slowly because it's a big file. This is also a scan of the turbo, which is in part of that. So this is the G25 660, so that's where the turbo is going to live. You can see I got some headers on here. Kind of designed those up already. They kind of look like, don't worry about the crude flange. Basically looks like that. Anyway, I could spend 6-7 more hours explaining all the stuff I did on this. I did. There's some stuff in this video that I did not explain what it was for at all. But I want to see. I want to see if anybody figures it out. If you know what you're looking at, it should be, if not obvious, you should be able to figure it out. But I'm going to do a different video on that. Why? But put in the comments if you can figure out what my secret plan is. I will be surprised, but please surprise me. All right, so here is the full compilation, or at least of what I have so far. Obviously, I will be adding to it, but I originally scanned the coupe body, so this is all coupe body stuff in here, but that's where the roll cage is going to live. The underside's a little bit more detailed, but you can kind of see where the inner fender is. If the scan's not complete on both sides, it just kind of fills it in with these blobs, which is not awesome, but that's kind of what it does. So you can kind of tell where the wheel sits in the fender and yada yada. Got my suspension geometry here. This thing at full minimum turning radius. Let's see if this works. There we go. So I got all my geometry in there, so I can just manipulate the steering rack to go whichever way I want. You can see all the suspension giblets in there. This is where the front bar suspension ties in. You can see the V-twin or the V10 is in there. That's approximately where it's going to sit. It might move back. I have like an inch plus of clearance to the firewall, so I might actually move it back a little bit. Good stuff on the underside. So there's my lower control arms. You can kind of see some of the exhaust system here. This is most likely going to get chopped off, and I'm going to go to liquid cooling instead of that thing that hangs out into the diffuser. I still need to scan my steering rack. This is just a stick right now, but you can see it goes right through the V10, the trough in between the pumps and the sump. But like I said, I think I can move that back maybe another inch. That'll help my weight distribution out a little bit. It's already in pretty good shape. It's 53, I think, % at the rear wheels. But yeah, this is, you can see the outriggers. If you watch any of my previous videos, that's what those are. See the header and the turbo sitting up here, axle shafts. Kind of all the appropriate giblets to make a car work. I mean, it's missing a few key components, of course, but my apologies for these views. I pretty much have to input to the mouse and then wait for 5 seconds for it to update. So, but this is a CAD spin, a bit notchy of a spin, but we're spinning. You can see where the frame rails come through and where the seat pan lives, and how the roll cage is kind of inside, where the window mechanism would be on the coupe. Obviously, the Fastback doesn't have any of that window mechanism stuff in there. So yeah, this is going to be the extraction from not only a jacking rail, but extract some air out from under the car. We'll zoom in here. We'll try to zoom in anyway. See how slow it goes. This exhaust system is obviously not quite done, but you can kind of see what I got going on here and get a pretty good idea of what I'm going to have to build in the next couple of months. Thanks for watching. If you like this content and want more, subscribe, like, and share.